Hi, we are continuing our discussion of wires and um, what we have done in the previous part. We looked at uh, estimating the resistance and capacitance. We uh, we looked at some of example, okay, to compute R and C, and we will continue with estimating or simplifying large, large RC networks. Um, and then move on to uh, the uh, crosstalk, which is basically main source of noise, and then repeaters, and then skin effect. Okay, so we're gonna look at those large RC networks. Okay, um, before we move to large RC networks, we had an example of the computing the flight time for a wire. Okay, and flight time um, is defined as um, uh, by definition as RC by 2. So for any wire, we need to compute the resistance, the capacitance, and divide by 2. So he says, let's compute the flight time for a wire and from the previous example, and we need to express this in terms of a delay of 15 picosecond. Okay, then he said, let's compute the flight time of 10 millimeter wire. Okay, so okay, probably need C. So the flight time equals R times C over 2. For 1 millimeter wire, the resistance is 800 ohms times 0.2 picofarad divided by 2. Okay, and uh, this uh, this is direct substitution. Okay, um, of the formulas. Okay, so if you do the math, uh, and this comes to, excuse me, this comes to 80 picosecond. Now, um, he said we want to express the answer in terms of, let's see, we want to express this delay in terms of fan out of 4. Fan out of 4, we computed this in the logical effort section, and we know that fan out of 4 has a delay of 5. So whenever you have an inverter which derives 4 inverters, then delay equal GH plus P. G is 1, H is 4 because we have 1, 2, 3, 4 load plus 1, and this equals 5. Now 5 what? 5 of tau, and I know that for 60 nanometer process tau equals 3 picosecond. which which means fan out of 4 equals 5 times 3 picosecond. This is equal 15 picosecond. Now, if I want to express that in terms of fan out of 4, this is equal to 800 picosecond divided by 15 picosecond, and this is equal to 5.3 fan out of 4. And just to illustrate here that this number that we got here, we plugged it right at the denominator here. Now, what happens if I have 10 millimeter wire? Well, the flight time equals 10 times 800 ohms, because this 800 is for 1 millimeter, times 0.2 picofarad times 10, because this is for just 1 millimeter. Divide that by 2, and this comes to 8,000 picosecond or 8 nanoseconds. Okay, and if I normalize this with fan out of 4, this comes to be 530 fan out of 4 delay. Fan out of 4. So, excuse me, fan out of 4. Okay, so this is basically the example that is being discussed at this slide. Okay, and now what we want to do is, whenever I have a large RC network, how can I estimate the delay from a start point to an end point? Let's just, for example, see these are, and so this might look ugly, but this is really close to reality, because wires, what happen when they connect devices, they tend to branch out to other devices. So the question is, how can I estimate the delay for these wires, and knowing that they kind of branch out? So I want to estimate the RC delay from this starting point to this end point. Okay, so let's see how we can do that. Well, first of all, what I need to do is to determine my main path. So from S to I, this is the main path. And the rule says the following, that that resistance that are off the path. Let's just get another color here. That resistance that are within the path, they are counted. The resistance that are off the path are short-circuited. That's the first thing we do. And second, what we do is that we compute the delay to every junction or every branch one by one. So the delay from S all the way to this point equals to what? Resistor R1 times, what's the capacitance here? It is C1 and C2. Notice, because this is short-circuited, plus. Then we move on to the next point, which is right here. Okay, so the next point right here, let's choose another color. So the delay for this one is, we have two resistance, R1 plus R3, R1 plus R3, times the capacitance in this node is C3 and C4. C3 and C4. Okay, plus now I'll have to use the last node here, okay? The last node here, which is this one here. So the resistance is what? R1, R2, R1 plus R2 plus R3. I'm sorry, R1 plus R3 plus Ri, because this is 1, 2, 3, multiplied by the capacitance in this node, which is Ci. No, that's not, this should be Ci, not C4, Ci. Okay, okay. Now, if we do another example here, uh, in this example, he wants me to measure the RC delay from this point to this point, which is referred to as TD3. Okay, so TD3, and for that, I can say that we have here is my main path. Okay, and this will be shorted. So I will compute up to this point first one. So this is R1 multiplied by C1 plus C4 at this point, C1 and C4. Then this second point, which is R1 plus R2 multiplied by C2, okay, plus the last one, R1, which is this one here. You see the path here all the way, R1 plus R2 plus R3 multiplied by C3. Okay. Now, then he wants me to compute the delay for between this point here and this point here. And in this case, I will short circuit this resistance and this resistance, right? But I will keep this one and I will keep this one. So TD3 will be equal to, or TD4 equals to, the first I'll measure this delay here, R1. Now I multiply it with C1, C2, and C3. C1 plus C2 plus C3, because that's the capacitance at this node. Plus, then I have this node here, which is R1 plus R4 multiplied by C4. Okay, so this is how I estimate the delays of complex RC networks. All right. Now every wire, since we have in a wire, when we estimate it, it has capacitance and resistance. The capacitance to charge and discharge this wire, we need energy to charge it and discharge it, and we know that this capacitance to charge it and discharge it, we have CV square. Half of that will be used for the rise, and half of that will be used for the fall. When we change, the rise is when we change the voltage from 0 to VDD, and the fall when we change the voltage from VDD to 0 volt. Now, if we have 1 volt and we have 1 millimeter, so we know for a wire which is 1 millimeter, C equals 0.2, C equals 0.2 picofarad, and let's assume we have a voltage of VDD of 1 volt. In this case, I can estimate the energy to charge and discharge this wire to be 0.2 picojoule. Okay, uh, 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 10 to the 9 second, uh, or 0.2 milliwatt uh, gigabits per second per milliliter. Okay, so Then the next topic that we are going to discuss is cross talk, and let's use here some whiteboard discussion. Okay, in terms of crosstalk, um, we need to differentiate between. So here is uh, here is crosstalk, and typically, let's say we have a wire. We refer to it as aggressor and um, victim. Both two wires will have a victim wire and aggressor. So aggressor and victim, and let's call this aggressor B and the victim wire A. Between the two of them, there is a capacitance, and we will look at two scenarios. And the first scenario is that victim wire is not switching, and the aggressor is switching. And what we notice is that there is a pulse that will be introduced in the victim wire. See, this wire is supposed to have 0 volt, but this pulse coming from the switching of the neighboring, we call it the aggressor, the noisy neighbor. Now, of course, this is undesirable, unwanted. So, so the victim wire here is not switching. So this is first case. And the second case, when aggressor, victim is, or when the victim is switching, and so in this case, so this victim is switching from, let's say, 0 to. So in this case, we'll consider various situation when the aggressor is not switching or switching with me or switching opposite to me. And the impact here will be more of impact on the delay for the victim. Okay, but here the impact will be more dangerous because we're introducing unwanted pulse on the victim wire. Okay, so two cases where the victim is not switching, the victim is switching, but impacted in both cases with its neighbor. Okay, now of course between the victim and the aggressor there is this capacitance, and we call it adjacent or coupling capacitance. Again, why is this capacitance? The simple answer is that between any metals in physics, between any metals with an isolating layer, you will have a capacitor. Okay, so that's this capacitor will try to uh, send impacts between wires and create noises in wires and excessive delays on wires, and that seems to be problematic. So we don't like crosstalk. This is something we do not like. Okay. Okay. So let's take a look at the first case here. The victim wire is switching. Okay, so this is the very first case where the victim wire is switching. So this is the victim wire A. It is switching. It is trying to switch, let's say, from 0 to 1. This is A. Now I'm trying to study the impact of B on A, and the victim here is definition is more of really a perspective um, way of looking at things, because if you look at the impact of B on A, we will call A victim and B aggressor. But if you look at the impact of A on B, then B is the victim and A is the aggressor. Now, so A switching, in this case, we will have three scenarios for A. A is not switching. A is switching with A, meaning the same direction, so 0 to 1. A is switching opposite to A, it means it's doing 1 to 0. And so here from 0 to 1 with A, and here it stays constant, not switching. So if A is switching, if B is switching, this is B here. If B is switching, then the impact of this capacitance, its effect will be just C adjacent, and we multiply it with this Miller effect of 1. But if B is switching with A, sort of helping A, then we don't see this capacitance, all right, and it's almost gone. Okay, so it is when we calculate the effective capacitance on A, we do not include it because it becomes 0. So it's just the ground and no capacitance for as far as A is concerned. Now, if B is switching opposite to A, so it is really impeding the switching of A, then we will double this and we multiply it by 2, and then the capacitance, the effective capacitance of A becomes ground plus 2 adjacent. And that's why we can see here that this here there's a 1 here factor, there is a 0 factor here, and there is a 2 factor. That's what we refer to as Miller coefficient effect. Okay, now let's take a look at the case number 2, which is whoops, sorry. Now, and in case number 2 is that we have this aggressor is switching, but my victim is not. My victim is not switching. A is not switching. Okay, and in this case, so this is switching, the aggressor. The victim is not switching. What happened is that if you do this voltage analysis, you will see that we will introduce a pulse of voltage here, and this delta V victim is computed by this formula. So basically, here you can see this is the aggressor. It is emulated as a voltage source, and the victim is emulated as a capacitor to ground here, but there is no drivers here. This seems to be pessimistic model, because what you are assuming that the aggressor has a very large size and the victim is having extremely small size, and that it becomes like almost like an open circuit here. Okay. A more realistic approach is to say, well, no, these are basically coming from drivers, so we have to put the resistor for the aggressor driver and resistor for the victim driver. And in this case, we have to adjust the previous formula so that we introduce this factor. Okay, so if you look at the previous formula here, we have C adjacent over C ground plus C adjacent multiplied by the voltage in the aggressor, on voltage divider rule. And now what we have here is that, excuse me, what we have here is that this voltage divider rule uses these capacitance with the differential voltage on the aggressor. Typically, this is equal VDD, by the way. As we say, this is pessimistic, so more realistic approach is to introduce this 1 over 1 k factor, where k is the um, the tau for the aggressor over the tau for the victim, and the tau for the aggressor is computed by resistance of the aggressor multiplied by the ground and the adjacent, divided by the R of the victim, which is here, and multiplied by the adjacent capacitance here and the ground capacitance, which is right here. This is more realistic approach, okay? And if we look at the graphs here, so this is how the aggressor goes from 0 to 1. This is the aggressor. So what happens if we don't have resistance and we model the driver and leave the victim undriven, which is basically this model right here, and as I say, it's pessimistic because it's not realistic. So what happened is that you will end up the victim doing like this, which is not true, by the way. But the victim has a resistance, and the aggressor has a resistance as well. And then you can see that the actual pulse that happens is much like so. So the question is do we care about this? Well, we consider this as noise. And if this is feeding to sensitive circuits, then this becomes a problem. Okay. So for static CMOS, noise typically resolved by absorbing these pulses in cascaded stages. So typically no problem. It is really when you are dealing with dynamic logic and memories, and these circuits tend to be very sensitive, and noises will probably cause a faulty circuit. Okay. Now, so the second topic or the third topic that we want to address is repeaters. And basically, why do we need repeaters? It is because when I have large wire and this large wire becomes over a huge load on this driver to drive it. So what we do, we segment this wire into smaller wires. So when we segment those, let's say we segment it into n sections. So in section, instead of I have the entire wire here of length of L, this is L here, this is L. I'm going to have smaller wires with L over n sections of the wire. Okay, and now I can start saying, let's have the repeaters here, and basically the repeaters I have an inverter, and I have another inverter. So notice that here I have the entire wire is RW. Since I have chopped it into n pieces, this becomes RW over n. This is RW over 2n and CW over 2n and CW over 2n. This is my pi model for the segment of the wire, and this is the capacitance of the wire of the receiving inverter, and this is the R over W. So R over W, because I'm sizing this guy to be W, so its resistance will be divided by W, and I'm sizing this to be W, so its capacitance will be multiplied by W. Now my question is, what is the optimum W and optimum N? So to do that, what I do is write I write the delay for the wire, for the entire wire, n times the delay of each segment. And each segment I can draw the RC circuit. This is for the pi model for the segment of the circuit. So this is the pi model of wire segment. This is the receiver. This is the driver. He's including here the diffusion capacitance. Now, once I model one segment, I multiply this by n to model the delay of the entire wire. Now, what I do is that I derive with respect to W and N and equal to 0, equate the derivation to 0 because I want the optimum L and N. And it turned out the optimum wire is L over N equal 2 times RC. Now these R and C, by the way, R and C are for the inverters. Over RW and CW, these are RW and CW, these are for the resistance and the capacitance of the wire. The delay of the wire, optimum delay per unit length, equals 1.6 square root fan out of 4 RWCW, and the optimum width is R of the inverter times the C of the wire over the R of the wire times the C of the inverter or the repeater. You can look up the derivation of these equations in your textbook. Now, so what it means here is that that an energy per length for a wire is 1.87 CW V square, meaning if we use repeaters, okay, so here is a wire. So wire energy, if we know repeaters and if we use repeaters, well, if you don't use repeaters, then the energy is CWV squared D. But if you use the repeaters, it is 1.87 CWV squared. Well, that seems to be a bad bet then. Why do we use repeaters? That increases energy. We don't use them just for fun. We use them because for long wire the signal degrades so much that cannot uh, uh, we cannot guarantee the integrity of the signal at the receiving end, and there will be excessive delay. That's why we must use repeaters. Of course, this is the price for that. Now, if you increase the delay by this much, you can optimize the sizes to so that you pay only a price of 30% increase in energy, because this is a premium of energy when you have optimum sizes, which gives you optimum design. Now, let's take a look at this example where we have let's see. Okay, so here is a repeater example where we compute the optimum delay for the wire. Okay, so and the W of the repeater, the size of the repeater, and the energy of the wire. Three things we compute in this example. So compute delay per millimeter, which is this is this is this is what we want, propagation delay of L. Assume that the wire in the middle of routing layer, which has 2x width, all of that means that I'm going to have a 200 ohms per millimeter resistance and capacitance of 0.25 picofarad. The fan out inverter assume 15 picosecond. Okay, so the optimum delay per unit length is obtained by evaluating this formula. Notice the FO is 50, FO for 15. The resistance of the wire is 800 ohms, and the capacitance of the wire it is 0.2 picofarad. Now, so this is basically what we achieve here. If we limit our delay I'm sorry, so this is the delay per 1 millimeter. Now for the W, we multiply the resistance of the driver times the capacitance of the wire over the resistance of the wire times the capacitance of the driver, and that uh, comes out to be, let's see, 18 microns. And for the energy, we evaluate this formula, and this comes to be about zero point 0.4 joule. In fact, I think it comes 0.37 picojoule per milliliter, per millimeter. Okay, and finally, the final topic here is skin effect. Okay, and the skin effect is an interesting phenomena when you run high-speed signals in wires. It turned out that if you have, for example, this is a cross-section of the wire, and this is the center of the wire, at, at high speed, electrons prefer to be close to the surface. For some reason, we don't want to explain it here. So the density of electrons are at the surface higher than the density on the core here. And the effect is that the electrons, they try to cram here and fight for space here, and that tend to increase superficially the resistance of the wire. Okay, this is at high speed. So people want, so that's the definition of skin effect. So people are interested to measure the depth in the conductor where the current falls off to E, this is the natural number, E to minus 1, which is 0.7. This is a measure, a certain measure of how quickly we lose the if this is E, for example, then the rest of the conductor uh, uh, seem or deemed unuseless because we are not using it that much. So this skin depth is computed by 2 times the resistivity over the uh, the um, the angular frequency and times permittivity, magnetic permeability of the dielectric. And for a free space, it is 4 pi times 10 to the minus 7 Henry per meter. Now, to estimate omega, we multiply. So basically, omega is typically 2 pi frequency, but for our chips, we try to have a simpler formula, which is 2 pi over 8.65 times the rise time of the signal. That seems to be easier to evaluate. This is an approximation, obviously. Okay, so if we look at an example here, okay, where we have a conductor, determine the skin depth of a copper. So the skin depth is equal to this formula. This is the skin depth, 2 times the resistivity over omega times the permeability. But we need omega. Omega is 2 pi over, this is how I compute omega, which is here, and it is computed in this formula. 2 pi over 8.5 times 20 picoseconds, and he told me that the rising edge or the edge rates are 20 picosecond. Evaluate all of this, and I get 33.6 radian per second. Okay, so I plug in this over here, and I get my skin depth, which is 0.99 micrometer, which means if I have a conductor of, let's say, a circular radius of 2 micron, I'm going to just only use the outer 1 micron in an efficient way to conduct. The inner 1 micro will not be used as much to transmit electron, because most of the electrons like to be at the surface. Okay, and this slide concludes the section of wire. Thank you very much. We'll see you and discuss other topics next time. Thank you.